Okay, let's take a look at lasers since we didn't have time last week. You have the page of notes. And really, the idea for lasers comes from Einstein, who thought that he was thinking about, okay, when you have an atom in an excited state, it's just absorbed in a photon and then the electrons jumped up. So then he said, okay, what happens if I send in another photon and strike this atom that's in the excited state with the photon that exactly matches what was absorbed? And what he showed was that if he did that, this electron that had jumped up would fall back down and it would emit a photon that it had absorbed that would exactly match the photon that it got struck with. So you'd now have two photons. And that's called stimulated emission. Stimulated emission, you're causing the excited atom to emit the photon that it absorbed before it probably would have emitted it on its own. And so now you have two photons that are going to be in phase with each other because so in phase or coherent or in step. Okay? So if you could somehow corral these two photons and get them to now hit another two atoms that are excited, then you'd end up with 4 photons, and then you could hit 4 more, and you'd get 8, and then 16, and then 32. And he imagined that you would get what he called an avalanche of photons. You get all these photons that if you somehow could corral, you could then send out in this really sharp beam. You would then have a laser. So there are 2 conditions that are necessary for this to happen. One condition is that the atoms that you're striking must be in an excited state. And the other is that you somehow have to collect the photons that are being given off. Collect them so that you could then hit other atoms with them until you end up with this avalanche of photons. Okay? So Einstein suggested this somewhere around 1917. One of the guys that gets credit for a laser is Theodore Minimum. I think he might have the patent, but I can't be 100% positive on that, but I'm sure one of you can Google it. And that was 1959 to 1960. So he was able to design a device that met both of these requirements, and so he gets credit for inventing it, and he called it a laser. Now, laser really stands for light amplification by stimulated emission of radiation. Okay? So light amplification by stimulated emission of radiation. And the atom that gives off the light, it's said to laze. Okay? And usually, so you put the atom into the excited state, usually by running a current through it. Okay? Now, flipping over. There are 4 characteristics of a laser. They're directional. What that means is the beam doesn't spread out. You know, with a flashlight, starts out as a small beam, but by the time it gets to the wall, it's like a huge circle of light. A laser, that's not how it goes. A laser starts out as a small beam, and when it hits the wall, it's still exactly the same diameter. Okay? It's monochromatic. We all know what that means. It has one wavelength, one frequency. Okay? It's intense. That's from remember intensity, and that's from the avalanche of photons. Intensity is the number of photons, how bright the light is. And it's coherent. They're all in phase with each other. They could be monochromatic, but not necessarily in phase. But in a laser, they're all in phase because of the way it's created. Now, sadly, lasers are really inefficient. When they were first made, they were about 1%. They might be a little bit better than that now, but I don't think we've gotten above 5%. So they're really still pretty bad. But nowadays, they have tons of uses. Surveyors use them when they're trying to build roads or bridges or tunnels. Right? The PEI bridge from New Brunswick, they use lasers to line it up so that because they started on either side, so of course they want to make sure they're going to meet in the middle. Same idea with tunnels. The tunnel that they're building from Campbellton over to Tignish PEI they've used a laser to plot it out. They did that with the one between England and France, too. All right, so maybe they're not building a tunnel from Campbellton to PEI. Maybe I was just checking to see if you were listening. But, maybe someday. We use them in fiber optics. That's how we send the signal. It's a laser beam. Spectroscopy, which is what we've just finished by exciting that should be single atom. Making holograms. They use them in medicine. We talked about laser eye surgery. Lots of times when you're having surgery, they can use a laser instead of a knife. They can go okay, and when you're having radiation for cancer treatment, it's really a laser beam. In industry, we use lasers to cut steel. We use it in welding. Maybe someday in nuclear fusion, if we ever figure out how to do fusion. Your CD players at home have lasers. Laser pointers in the classroom, or kids that are being annoying. All kinds of examples of uses of laser today. But back in the 1960, when it was created, the line was a laser was a solution looking for a problem. So when it was invented, it was like, oh, this is really cool, but I wonder what we'd use it for. So we found tons of solutions now, but back then we didn't have any uses, but they realized this will be useful. Now we just have to come up with a problem where it can be a solution. But certainly medical people would tell you that they're definitely worth it. Okay, so no calculations with laser, it's just theory. Okay, and that is really the end of the quantum unit, which means we are now going to start the nuclear unit. Woohoo! Which is really cool. So up until now, we've been talking about the atom, but really we've been concerned about what are the electrons doing. It's now time to say, okay, but what about the rest of the atom? What's going on inside the nucleus? Remember our good friend, good buddy Rutherford said it was the core of the atom, the concentration of the positive charge, the concentration of the mass. He was right. He was wrong about what the electrons did, but he was right as far as we know today, at least, what the nucleus is. Okay? There's a word called nucleons. I don't know if you've heard of it before, but it's just all the things inside the nucleus. So they're called nucleons. And of course, we know what's inside the nucleus. They're the protons and the neutrons. The protons have one positive elementary charge, and the neutrons are neutral. And they have roughly the same mass as a proton, but no charge. Roughly the same mass. The mass of a proton, and I don't have it written down there for you, but it's 1.673 times 10 to the negative 27 kilograms. And for a neutron, it's 1.675. times 10 to the negative 27 kilograms. So roughly, it only differs at the 30th decimal place, so that's not too bad. Okay? We've talked about atomic number last unit. Atomic number is the number, we used it as the number of electrons when we were doing the electron configurations. You saw me writing the letter SED, but I never actually said it was the atomic number. I guess I was probably assuming you had used it in chemistry. But we don't usually say the atomic number is the number of electrons because that can change when they become ions. So the atomic number is really the number of protons. If the atom is neutral, it will also be the number of electrons. But not all entities that you will come across will be neutral. So we call it the number of protons. And if the number of protons change, the element changes. Okay? So each element has a different number of protons in its nucleus and therefore a different atomic number. If the atom is neutral, it will match the number of electrons. So atomic number is said, and then there's mass number. And the mass number is the number of protons plus the number of neutrons. Unfortunately, its symbol is A. Might have made a lot more sense if atomic number was A and not said, but it isn't. So A is the number of protons plus neutrons. So if you did A minus said, you would